Thank you.
Hello, everyone. Can you hear me?
Yes, we hear you well and we see your screen. Great. So you can go, maybe you
Awesome.
want to try do full screen view, I guess, right now.
Yeah.
Yeah,
Okay.
go for it.
Awesome. Good evening, everyone. It's nice to meet you again here. And my name is Abdul-Malik Saiid, and I work under the supervision of Dr. Philip Kurian in the quantum biology lab at Howard. And I am a graduate intern currently. And I would be happy to present to you an ongoing work, which is very interesting, related to an application of the Kohlrausch function to the ultrafast transient absorption spectral kinetics. So my work or our work seeks to investigate whether the well-known stretch exponential function, which is basically an exponential decay function that has a fractional power law, i.e. it has an exponent. It's the normal exponential function that we know, but this one has a fractional exponent, which I'll be explaining later, which is the stretch exponent. So we try to investigate that this decay function can emerge naturally from the collective quantum optical behavior of microtubules. So to be specific, we study the ultrafast transient absorption decay measured experimentally at different wavelengths, which I'll be pointing to later in the results. And then to observe the non-exponential relaxation that can be explained directly from the collective radiative edging spectrum of the microtubule. So where do we get this collective radiative spectrum? So it is something we get from the 1GFF microtubule structure that we construct from using the non-Hermitian effective Hamiltonian. So what we do is we have that structure that is built from the 1GFF tubulin dimer to form a microtubule, and then using the effect non-Hermitian effective Hamiltonian, we model this system, and then afterwards we diagonalize it to get the complex eigenvalues, i.e. the solution to the system. Now from the solution, we know that the E is the excitation, and then the collective decay is the gamma. Now, this gamma from the earlier structure that I described, that is from the observed microtubule data, experimental data, we extract a reformulation of the stretch exponential function that I explained. And then from that, we realize that the inverse Laplace representation gives us the distribution of the decay rate from this microtubule data that we have, which is the tubulin dimer structure, 1GFF. So we obtain this new, should I say, optical density from the one that we already did that I call the IFIT. So this time we have two. Now, in order to study this finite system, we need to discretize it. So we undergo some discretization to get it in this form, which is the summation, which is the normal Riemann sums that we know. Now, after this formulation, everything now boils down to somewhat of a curve fitting, not necessarily a curve fitting, but we intend to observe experimentally that whatever derived the underlying distribution of the collective decay rates in the microtubule is the same as the observed experimental decay that we see, which mimics the Kohlrausch decay. So after the construction, we did some analysis, and then you can see from the results that I have here. Now, this is a plot of the various experimental microtubule data, and then the fit that we reformulated using the stretch exponential function. And if you can see, I know it's a little bit little, but if you see the various wavelengths at which we probed, which is from 295, here we do have a 285 as well. So from 285 to 325, you would see that the wriggled lines are the experimental data, and then the dashed lines are the fits that we have that describes the stretch exponential behavior we have, which is the non-exponential relaxation. Now, from that, our focus was just on the 295 nanometer wavelength. So what we did was, from our reconstructed optical density, which is from the inverse Laplace representation, we apply several spiral numbers, which is 4 spiral, 30, 50, 100. And then we see how it mimics the non-exponential relaxation that we see in the experimental data. And you can see from the plot that I'm pointing at, from 0 to 1600 picoseconds, how it closely mimics the two regimes that we see in the non-exponential relaxation, which is the super radiant state, and then the sub-radiant state, which is a slow decay state. So it is remarkable to find out that the mean square errors that we have scales from orders of 10 to the power negative 7, and then increases to 10 to the power negative 9, which tells us that there is a close fit to whatever phenomenon we observed in the experimental data. And so we are hoping to be able to describe better the intermediate regime, which you can see pointing here, apart from the super-radiant state and the sub-radiant state, whether or not the distribution decay rates that we constructed, i.e. the inverse Laplace representation, can closely describe as well the intermediate regime. And then part of the future works is that we intend to construct something we call the spectral density, which gives us some sort of a geometric representation. And hopefully we hope to find a correspondence with the refined distribution that we constructed this project on. And so that is what I have for you today. And I'm hoping to take any questions from you. Thank you.
Question for you. You want to take some